Hey there, math fans. Continuing our little series on vector facts. Here I'm going to talk about a couple 2D things that often cause students trouble. Um, as I said in the previous video, the idea of working with vectors instead of slope is simply because we have to when we move to 3D. But a lot of those ideas still could be used in 2D. And in talking about these couple of things, and we'll talk about what to do with slope and how to turn it into a vector and what to do with angles, those are important things in applications because we often have those two pieces. So in terms of slope, it's a fairly quick idea. If you have a line where the slope is m, then what in the world does that mean about the changes in x and the changes in y? It's a fairly quick observation. And the observation is that, well, the rise over the run, the change in y over the change in x, has to be whatever m is. Now, the problem for students is that leads to ambiguity because there's an infinite number of things that do that, and students don't like having choice. That's a pretty uniform thing I've found in all these math courses. So let's do a quick example. What you see below is the graph of the cubic graph. That's the black curve. And I drew a tangent. So there's a tiny bit of calculus that's going to appear here. That's the derivative. I always tell students, if you don't remember anything else about calculus, you should remember that the function tells you the height and the derivative tells you the slope. So for example, if I'm standing on this curve at 1, this is x equals 1, and I want to know the height, it's going to be 1 cubed, which is 1. If I want to know the slope, it's going to be 3. So if you didn't catch that, that's one of the main things in calculus, that we can very quickly get both of those things. Without calculus, we wouldn't be able to get the slope. Without that, we wouldn't be able to find max and min and all that stuff. But I didn't intend to do a full review. The review question is, how do I find vectors? And there's a bunch of things we're going to learn this term about things we can do once we have vectors. So a natural question is, how in the world could I find a vector that points this way? And I'm going to show you some visuals in a second, but sometimes it's useful to have a vector that points somewhat inwardly as well. We call this a normal vector or an inward facing normal. That's not a major topic for today, but it will be something in chapter 13, so I just thought I would mention it here. And we would call this a tangent vector. Now there's an infinite number of tangent vectors. You could even have a tangent vector point the other way. There's an infinite number of normal vectors. You could have the normal vector point the other way. Normal is just a fancy word for perpendicular in 3D. Not very fancy, I guess. So we need a vector with slope 3. That's fairly easy to do. So let's just quickly talk about that. How can we do a vector that has slope 3? Well, you could make this 1 and this 3. Is that the only answer? No, you could do 2 and 6. You could do 10 and 30. All of those would be correct. So 1, 3 is the most natural choice, but another reasonable choice would be 10, 30. Now, a lot of times what we try to do is make it a unit vector, and to make it a unit vector, you get this messy thing. You find the length. Now, the length of this vector is the square root of 1 plus 9. The length of this vector is the square root of 100 plus 900. But it turns out if you write the following, they are exactly the same. If you take the first one and divide everything by the square root of 10, it's the exact same thing that if you take the second one and divide everything by the square root of 1,000. So that's why it doesn't matter what you're starting with if your goal is to get a unit vector. And if that's the case, let's just use 1, 3. I get tons of questions. People ask me why I used 1. It was my choice. So this would be a unit vector that points the direction we're going. This would be a unit vector that points the opposite direction we're going. And so I think there's a couple homework questions that ask that. Find those two unit vectors. Now, a quick comment about the perpendicular slope. The perpendicular slope is the following. So in this case, the perpendicular slope would be negative 1 over 3, if you don't remember that fact, the negative reciprocal fact. So what can we do? It's the same thinking. Now in this case, I would like this to be a 1 and this to be a 3, and I would like one of them to be negative. So this is sort of the equivalent. Let's get rid of the unit vector stuff because it's confusing me. Let's rewrite a simple vector 1, 3. And now I'm going to give you a vector that's perpendicular to it. 3, 1 with one of them being negative. That's it. Here would be a vector that points the opposite way in his tangent. So these two are tangent. Here would be a vector that's the opposite way to this one. These are tangents. These are normals. Let's quickly show you a visual of that so you can see it. Now, I did not make them unit vectors, and you're going to see why that's kind of messy, but here we go. I'm going to show you this moving along, and you can see how seeing both of those tells me a lot about my motion. I'll make this go slowly and animate it. So let's go back a little bit. Here we go. Turns out the length has something to do with the slope itself, and you can see why if we're watching this thing move, it might be nice to have this vector that points inwardly and one that points tangent. If we don't want them to be getting longer or shorter, we'd make them unit vectors. There you go. And you could get the ones that point the other way if I only plotted 2 of them. So that's a useful little thing if we're going to take our formulas from 3D and use them in 2D. And we will see pictures like that, but in 3D there's a third vector which points like the direction our head is pointing. Okay, separate little thing. So that's a really fast thing that students forget later in the term. So quick thing about angles. Let's get rid of some of this. So if you're being pulled on a wagon, and here I have Butch pulling me this way with a force of, 6 pounds. So he has this vector 6, 0. Let's call that vector B. And then Harry is pulling this way at some given angle. And maybe he's pulling at, 3 pounds. That doesn't tell me the vectors. I know how to add them together if I can get them. So we often have this issue of, well, what if someone tells you this is 60 degrees and you need the actual coordinates? That requires you to do a little bit of trig. This usually scares students to death, but you can do it. If you need me to do a review on trig, let me know. I have some of this posted online. But you should know, if you know those 2 things, you also know this, and you also know this for free. That was the whole point of trig back when you learned it. Okay, this is what we're calling the change in x. This is what we're calling the change in y. And so we can say cosine of 60 degrees. And we need this to become second nature at some point, this term, if it hasn't already become second nature. And I just find various students have different holes in their background. That's something you can fill. If you need me to review, tell me. All right, at that point, we can figure out what those things are, what the change in x. So the change in x is going to be 3 times cosine of 60. The change in y is going to be 3 times sine of 60. And this works as long as this angle is measured from the positive x-axis. So it even works in other quadrants, if you forgot that. You do need to remember these values. They're in my handout from the first day of the class. But again, that's probably best for me to do in a separate video if you want me to. I think I already have some things like that, but let me know if you want me to find it. Or maybe someone else can and put it in the comments. So there we go. The other thing is you should know that the y is bigger, whatever. Okay, so we get the vector A is 3 halves, because it's 3 times a half. The vector v is the square root of 3 over 2 times 3. Forgot my 3 there. So now if you wanted to add those 2 things together, now you can add them component-wise. So the hard part is not the adding. So it's going to be 6 plus 3 halves, and it's going to be 3 root 3 over 2. Sorry, I ran out of space there. That's it. That's the direction I'm going to be pulled. And then I can do some more trig, which I'm going to leave my students to do. I did this in class, to find out what the length of this resultant vector is. and what angle it makes with the positive x-axis. But let's show quick visuals of that as well. Here it is. I made up those numbers, but it's the way you're being pulled. So I made this silly, me being pulled on a scooter. If you missed this, I think in my previous video I had one of the numbers off. So like one of the vectors was slightly off. I'm going to leave it. But there's that sum. That's the direction I'm going to be pulled. I don't know how my animation goes. Yanks me that way. There you go. So there's some 2D vector facts. Hope that was helpful.